Hey guys, so today we're going to be learning about how to take measurements and how to know whether or not you're sure of your measurement and how many decimal places you're allowed to carry it out. So lots of things today about how to measure and when we measure and looking at uncertainty in measurements. So we're going to start out with an example of this leaf. So the line here is representing how to measure the leaf, and so we're taking the measurement. And we know by looking at it, I can see that it's bigger than 3 but less than 4, so I feel confident that the first number is going to be a 3. My first number is going to be a 3, and then the second number is really a guess. So I think that it looks like 3.6 inches. Maybe you think it looks like 3.7. We could argue about it all day, but we're both just guessing. So we know that it's bigger than 3 and less than 4, but after that, we're really just not certain. That is the uncertainty in this ruler. Now we could get a more certain ruler. If I look at this ruler, it has additional markings on it to indicate additional portions of the length. And so now if I look at this leaf, I can see that it is 3, and then I can count 1, 2, 3, 4, 5, and then the line ends before the tally mark for the 6, but pretty close to it. So I feel like now I know that I'm definitely 3.5, bigger than 3.5, less than 3.6, and so I'm going to guess 3.59 inches as the measurement of my leaf this time. This is how we determine significant figures. We consider how many values did we know and which ones did we guess about. So a significant figure are all of the figures in a measurement that you are certain of, plus the next or the last figure that was an estimate and is uncertain. So in our first measurement, we got a value of 3.6 inches. 3.6 inches has two significant figures. 3 is significant, 6 is significant. 3 we're sure of, 6 is a guess, both significant figures. In our second measurement, we got 3.59. 3.59 has 3, 5, 9, 3 significant figures. So depending on the way that you measure, what number is certain and what numbers are guesses, we can come up with different numbers of significant figures. So if we want to have a more certain measurement, then we need a more accurate measuring device. We might want to choose or prefer to choose a ruler like this bottom one over a ruler like the top one because of the certainty in the measurement that it gives us, and that's a really significant thing in chemistry. So when it comes to determining significant figures, there are a series of rules to help us determine how many significant figures there are in a particular measurement. So we're going to go through those rules now together. The first rule says that all non-zero numbers are significant. All non-zero numbers are significant. That means anything that is not a zero does in fact count for the counting of significant figures. So a value like 314 has 3 significant figures because there are 3 integers, 3, 1, 4. A number like 72.938, again, all non-zero numbers, all significant, easy, 5 significant figures, no issues there. Nice. Now, our zeros are where things get a little bit different. Sometimes zeros are significant and other times they're not. They're just placeholders. And so one of our jobs is to determine, is the zero significant or a placeholder? And there are 3 rules to help you determine the significance of a zero. First rule is that zeros between non-zero numbers are always significant. This is when you have non-zero numbers as bookends, okay? So a number like 30007 has the 3 and the 7 as bookends, and so everything in between automatically is significant. So a number like 30,007 would have 5 significant figures. Similarly, even if there's a decimal place, a number like 2004 would have 4 significant figures because the zeros between non-zeros are still bookended by non-zero integers, and so they are significant. Lastly, 108.0203 would be considered to have 7 significant figures. 1 is significant because it's not a zero. 8, 2, and 3, all non-zero numbers. And all 3 of our zeros are bookended between non-zero numbers. So all 3 of them would count. So 4 non-zero numbers, 3 zeros, 7 total significant figures. The next rule says that zeros in front of numbers do not count. This is like in an odometer in your car. Old cars would have an odometer that might start out 0, 0, 0, 0, 0, 0, 1, 0, and that would mean you had 10 miles on your car. Or if you've ever gone to Steve's or a place that writes your receipt on paper and then tears off the bottom, that number that they tear off the bottom usually has a whole bunch of zeros in front of it. But when they go to call out your number, they don't say 0, 0, 0, 0, 0, 5, 1. They just say 51 because all of those front zeros just really don't matter to the value of the number. So zeros in front of the number do not count. And that's really easy if there's no decimal in the number. People don't really get confused by that. So a number like 0043, these first 2 zeros would not be significant. So a number like this would just have 2 significant figures. The trickier one is when you have a number like 0.00216 and you just want those front zeros to matter because they're in a number that has a decimal place. The truth is, though, that those zeros do not matter. They are still leading zeros. They're just placeholders, and we can just as easily get rid of them. So we end up with 216, and that has exactly 3 significant figures. So this is a good time to start thinking about scientific notation. So what we're going to do now is we're going to look at this number, 0.00216, and we're going to start introducing this concept of how scientific notation might help us write a number like this. So 0.00216, we want to write that number in scientific notation. So the first thing that you need to know when you're going to write a number in scientific notation is that there can only be one integer to the left of the decimal place. Another way to say that is that the first number has to be something greater than 0 but less than 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, those can all be in the front, but not 10 and not 0. So in this case, I have a 0. That's not going to work. So I'm going to have to move my decimal place until I get one number to the left of the decimal place. So I get 2.16. Now that I have 2.16, I'm going to say times 10 to the, and then my exponent is going to give me directions about how to move my decimal place. So if I wanted this number, 2.16, to become 0.00216, the question is, how do I do that? Well, I would need to move my decimal place 1, 2, 3 places to get there. That means that this is times 10 to the negative 3rd power. If I have to move my decimal to the left, to get out of scientific notation, my exponent is negative. And then similarly, if I have to move to the right to get out of scientific notation, my exponent's going to be positive. But now that I have this number in scientific notation, it's really easy to see that what we already knew, that the number of significant figures in this value is 3. Our last but not least rule about zeros is that zeros at the end of a number count only if there is a decimal in the number. So zeros at the end only matter if there is a decimal. This has to do with exactly how we would round them. So a number like 1,400, no decimal place, has only two significant figures. The 1 and the 4 are significant, but the zeros at the end, because there is no decimal place, those numbers are not considered to be significant. Only 2 for 1,400, no decimal place. If we add the decimal place, then we add the assuredness that those are zeros. If we have a number like 1,400 with no decimal place, what I'm really saying is that this number is somewhere between 1,350 and 1,449. These numbers, 1,350 to 1,449, would both round to 1,400 or 1,400. That's why when we're dealing with money, we don't leave off the decimal place. You gotta put the decimal place. If you just said 1,400, someone could very easily come up to you and offer you 1,350, and truthfully, that's all you've asked them for. So in money, we always put the decimal place because the decimal place indicates that we mean exactly $1,400, $1,400. No funny business, no rounding, just exactly that number. So a number like 1,400 with a decimal place has 4 significant figures because we are being very exact. The same thing happens with 14.00. 14.00 specifies all the way out to the change that we are talking about $14 exactly. Not 1 penny more, not $13.99, $14. That's what those zeros at the end are showing us. So that number would have 4. And last but not least, $140.00 means $140 flat, not $140.01, not $139.99. It means 140. And so it is specific all the way up to 5 decimal places. So now we're just going to take a second and we're going to look at what these numbers look like also done. So first we're going to start by looking at the difference between 1,400 no decimal place and 1,400 decimal place. So first let's look at this first one. What we're going to do is we're going to do the same thing. We're going to make our leading integer one number to the left of the decimal place, only 1. So this is going to be 1.4 because those are the only 2 significant figures in my number. And then I'm going to say times 10 to the, and I'm going to put a number that's going to turn this into that. And so often what we look at is that we would need to go from here, we would need to go 1, 2, 3 places to the right in order to make it 1,400. Remember, when you move to the right, your exponent is positive. And so this is times 10 to the 3rd power, 3 places to the right. The other way to think about it is if you're trying to make your number bigger, you're moving to the right. If you're trying to make it smaller, you would move to the left. Okay, so 1,400 decimal place gets written 1.400 because all of these are significant. I still need my number between 1 and 10, and I still want to say times 10 to the 3rd because I still want to move 1, 2, 3 places to replace my decimal place back where it belongs. Okay, so let's look at the other 2 examples, 14.00 and 140.00. Both of these, like the other ones, become 1.4. 1.4. The question is, how many zeros do they get, and what's the exponent? So this one had 4 significant figures, so I need to keep 4. 1, 2, 3, 4. Times 10, and I only need to move 1 place to get back. So times 10 to the first power. For my second example, I have 1, 2, 3, 4, 5 significant figures. So I need 1, 2, 3, 4, 5 times 10 to the, and now I'm going to move 1, 2 to the right to get back to 140. So times 10 to the second power. So this is how we're going to move decimal places in order to put our values into scientific notation. So now we're going to do something that I think is kind of fun. We're going to do some mixed practice to try to see if you know how many significant figures are in each one of these values. When we do this kind of mixed practice, obviously the non-zero numbers are all going to be significant, but we're going to have to look at each of the zeros to determine their significance. So let's start with this top one, 30,604. For this value, 3, 6, and 4, of course, are significant. And in this case, the zeros are between non-zero numbers. We have that bookend thing happening. And so we know that all 5 are significant figures. For our second value, 2030, we know that 2 and 3 are significant. We know that the first zero is significant because it is bookended between non-zero numbers. So the question is, with this last zero, is the last zero significant? No, the last zero is not significant because there is no decimal place in the number. It would only be significant if there had been a decimal place in the number. So this has 3 significant figures. Our next one, 0.0610, leading zeros, remember, are never significant. So 6, 1, and 0 are all significant. The end 0 is significant because there's a decimal place in the number. So this one has 3 significant figures. Continuing on, 04.080300. Our leading zero, once again, not significant. Leading zeros are not significant. The 4, 8, and 3, of course, are. This 0 is bookended. This 0 is bookended. And my ending zeros are after the decimal place, so they all count as well. So this time we have 4, 0, 8, 0, 3, 0, 0. Back to 7. 7 significant figures. And now last but not least, 2.30 times 10 to the 5th. When a number is in scientific notation, all of the guesswork about what's significant and what's not has been taken out for you. Everything that's written counts. 2.30, all 3 of those are significant. And so even though this is a very large number, it only has 3 significant figures. If we take it out of scientific notation, it would look like this. This number would be 230,000. That's 230, and then we move the decimal place 5 places to the right. 1, 2, 3, 4, 5. So that makes 230,000, but with only 3 significant figures. So this is a way that scientific notation can help us represent a number with the appropriate number of significant figures. If we put a decimal place here, that would indicate that we had 6 significant figures, and that is not true. If we don't have the decimal place, that indicates that we only have 2 significant figures, and that is not true. So the only way to write 230,000 with exactly 3 significant figures is by enacting scientific notation. That's why scientific notation is so helpful for us in science. We're going to practice by writing these top 4 numbers in scientific notation. So I have some examples up here, and we're just going to be putting these numbers into scientific notation. So remember, the first step is always to make the first number, to make the integer greater than 0 but less than 10. So we start with 3.0604 times 10 to the, and now we need to figure out how many places would we need to move it. So if I was here, I would need to go 1, 2, 3, 4. 4 places to the right. So I know it's a positive 4. 3.0604 times 10 to the 4th power. For the next one, again, make my numbers something between 1 and 10. So 2.03 times 10 to the, and this time I have to be very careful to make sure I put 1, 2, 3. So even though this 0 is not significant as an integer, as a specific number, it is significant as a placeholder. Imagine if I owed you $2,030 and I was like, well, let's just make it an even 203. That won't work, right? I need to make sure I keep my place values, that I make sure that that number stays 2,000 and doesn't become 200, okay? Okay, next one, same thing. I'm going to make my number something between 1 and 10. So I'm going to make it 6.10. And this time, in order to move it back, I have to go 1, 2 to the left. And remember, when we take it to the left, that means that this is to the negative 2 power. Okay, so when we move to the left, we're taking it to the negative 2 power. And then my last one, well, this one is already in scientific notation. All I need to do is get rid of this 0 that was not significant. So 4.080300, that is a number between 1 and 10. I don't have to do anything to that. If I absolutely had to, for some reason, I could say times 10 to the 0 power. That means don't move the decimal. That's what it means, okay? All right, so let's go on and do some rounding. So rounding is definitely one of those things that everyone feels like, well, I know how to round. Why are we learning rounding? And then it comes to the test, or far down the line, we're doing molar masses and you have to round, and a small mistake ends up causing a big error. And so I like to take just a moment at the beginning of the semester to just remember how rounding works. So we're going to look at a famous number. We're going to look at pi. So pi, this is pi and the first 30 decimal places of pi. Many people memorize 100 decimal places out. Maybe that's something you've done. But pi can go on and on forever, right? The number that never ends. But if you look in your calculator, it typically gives you the value of pi as 3.14. This is a rounded value. So what they've done is they have taken 3 significant figures. 3 is significant, 1 and 4 are significant. And then they identify a deciding decimal. The deciding decimal tells you what to do with the number you're rounding off. So if I were to identify 3 significant figures in pi, I would find 3.14. If I wanted to know what my deciding decimal was, I would look for the numeral that followed the last significant figure. So in this case, it's a 1. And then I apply the rounding rules. You guys know how rounding rules works. If the deciding decimal is less than 5, then we stay. I know a lot of teachers say that you round down. I don't like that terminology. I like stay, hold. If your deciding decimal is less than 5, then hold. Stay where you are. If the deciding decimal is greater than 5, then of course we round you on up. A number like 3.141 becomes 3.14 when rounded, because the 1 is less than 5, so we stay. There are lots of rules that decide where to round off, how many decimal places or how many significant figures you should keep. I have settled in this class, intro level, high school, regular chemistry. We're going to just round them off at 2 decimal places. Those particulars of rounding rules you can learn when you get to the appropriate math level. You're not all there right now. So I'm going to leave the rule as 2 decimal places. That's what we're going to do. But for this test, you will need to round off to the number of decimal places I tell you to, or the number of significant figures that I tell you to on the test. So that's what we're going to be practicing today, is rounding off numbers to the number of significant figures that you're asked to. And so we'll go ahead and start that here. With a number like 32.764, we want to round to three significant figures. So the first thing we need to do is identify our three significant. So my three significant figures are 32.7. And now I just identify my deciding decimal. Remember, the deciding decimal, or the deciding digit, is the number that comes after my significant figures. So in this case, the number is a 6. 6 is greater than 5, and so we round up. And so our rounded answer is 32.8. Simple, right? All right, let's practice some. As we look at these answers, or these questions, we start with 15.6789, and we want to round that to four significant figures. So 1567 are our significant figures. That means 8 is the deciding decimal. And since 8 is greater than 5, we're going to round up. And so our final answer is 15.68. 15.68, because the 8 rounds the 7 up. Our next number is 217.5, and we want to round to three significant figures. So once again, we start by identifying three significant figures, 2, 1, and 7. Once the significant figures have been identified, we can identify the deciding decimal as the next value. In this case, that means it's a 5. 5 rounds the 7 up. Our deciding decimal is 5 or greater, so it's going to round us up. 218. For our third value, we have 5,234, and we want to round this to three significant figures. So what do? We find our three significant figures. 5, 2, and 3 are all significant, and that means that 4 is our deciding digit. Since 4 is less than 5, we're going to go ahead and hold. So we say 5, 2, 3, and hold. Does that make sense? Does it make sense that 5,234 would round off to 523? No, that does not make sense. I need my placeholder. 5,234 rounds to 5,230. For our next value, we have 0.003692. We want to round that to two significant figures, so I need to find two significant figures. Remember that zeros before my first integer are not significant. So now my deciding decimal is a 9. The 9, of course, rounds us up, and so we get for an answer 0.0037, two significant figures. Next we have 19.97. This one gets a little tricky, and it gets people all the time when they're working on rounding for atomic mass. 19.97 to three significant figures. So I've identified my significant figures as 19.9. And my deciding decimal is a 7. Now this is greater than 5. So the 7 is going to make the 9 a 10. And we have to carry the 1. And that 1 makes this 9 a 10. And we have to carry the 1. And so our final answer becomes 20.0. 20.0 is 19.97 rounded to three significant figures. And that makes sense, because if you were 19.97, you would round to 20. So for both of these examples, we're looking to get three significant figures out of them. For the top one, you might just add a significant figure. You're really not supposed to do that, but if you were told on the test that you must, then fine. You can add your significant figure. The more important one here is this 2,000 taken to three significant figures. If I want 2,000 to have three significant figures, I have to use scientific notation. I can't otherwise make it happen. So if I'm going to put it into scientific notation, remember a number between 1 and 10. I want to have three total significant figures, which means I need two more zeros. And now, real easy, you should be able to see the solution now. Times 10 to the third power will enable me to take this back out of scientific notation. 1, 2, 3, 2000. All right, you guys, that was some good work for today, reviewing old things that we should know and new things that we're maybe learning today. And I will see you guys tomorrow for some practice in class.